Okay, maybe we can start. Today we are very happy to invite Dr. Jemin Hwangbo to give us a talk on learning-based control for the robots. I'm your host today. My name is Yanran Ding. I'm assistant professor at the robotics department at University of Michigan. Dr. Jemin Hwangbo is an associate professor at KAIST, and he earned his bachelor's degree from the University of Toronto and his master's and Ph.D. degree from ETH Zurich under the supervision of Professor Marco Hutter. Dr. Hwangbo is one of the pioneers of using reinforced learning for locomotion. His work on learning agile and dynamic motor skills for robot was published on Science Robotics and enabled the quadrupedal robot animal to take a hike on the Alps. So we are very excited today to have Dr. Hwangbo to give us a talk. So without further ado, let's get started.
Okay, thank you for the introduction. So let me begin. So if you're wondering what I've been working on at KAIST, we're actually building these Lego robots. So just like Professor Park, Heron Park, we love designing the robot, making it. Then we do the control, we do the navigation, so we do the whole pipeline, the whole spectrum of Lego robotics. And yeah, so we have Raibo 1, which we built about 2-3 years ago. And the latest one is Raibo 2. And I'm going to talk about both of these robots. And of course, mainly the control, how we control these robots. Yeah, before I really begin, I want to introduce the physics engine Raisim that I developed. To be honest, I'm not working hard on it anymore because it's already working well for us, and yeah, I'm just using it as a user, and all my students and many others around the world. And yeah, it's a physics engine, but it's specialized in very high speed articulated body simulation. So it's a bit faster than Mujoko. And but the real difference is that we do hard contact simulation, so you don't see the penetration at the velocity level. So every time we solve a problem, and that gives a solution that guarantees zero penetration velocity. Okay, so that's the main difference between Mujoko and Raisim, and of course, Raisim has all these basic functionalities for like the sensor simulation, mesh simulation, and so on. So if you're interested in, as an academic, you can just download it for free. You can register and download it. Okay, so yeah, it's kind of bad drawing, but I like when I started at KAIST, I wanted to solve a problem like this, and I just drew this on my iPad, and basically what I want to do is running locomotion on discrete terrain. So here, what I mean by discrete terrain is there is a discrete region that that the robot can step on, and if the robot steps on somewhere else, it will fail. So yeah, of course, you step on the water, then you will fail. So there is discrete like footpaths or the region that you can step on. Then I mean you can also call this a stepping stone. Is what maybe this discrete foothold or discrete environment is the superset of stepping stone. It also has like different angles and more complex environment. People have been working on, also this is not my work, but people have been working on to solve a problem like this. And this is one from CMU. And what people have been working on is try to input the whole map into a network and hope that we get an output from the network. Okay, and I'm going to explain that why this is actually a very difficult way. And you might know, but actually, this path planning problem actually doesn't work like this. And one of the big reason is that if we look at the map and try to figure out the best path, what we actually do as like what we as a human do is that we look at different paths and we evaluate the path rather than just looking at the map and figuring out the best path. Okay, so for example, if you have a maze, so you want to solve a maze and you cannot give an answer right away just looking at the maze. You have to try once, follow the path, and see that that is blocked. Okay, that is blocked. Then you try another path and see if it's blocked, and so on, right? So you will do this iterative way, right? Because just looking at the map is very difficult to figure out the best path, and that's also due to the how this problem is structured because uh, the network, so in the environment, there can be multiple candidates for the best path, and this is highly non-convex problem, right? So you can take one path that will give some low cost. You can take another path that will also give you low cost, but it's very hard for the network to learn this highly non-convex multimodal function and just give out the single output. Like it's a highly non-convex problem, multimodal cost function, and you want the network to just output the maximum of that function. And this is very difficult for a network. So what we did instead, of course, what we want to do is sampling-based way. But let me share the video and then we talk more about it. So um, so in this work, I mean, this is more about the control part. So this paper is actually has two parts where we do the control and where we do the planning. And actually, they have to work together. We cannot really separate them. So you need to train the planner together with the controller. And but if you just try to train one, it doesn't work. Why? Because they are dependent on each other. The controller uh, uh, the performance of the controller is highly dependent on the planner because the planner gives the controller where to go, right? And you want to train the controller in a way that follows the planner's path very well. And for the planner, you cannot train a planner without knowing the characteristics of the controller. So you have to know exactly how this controller behaves, then you can do the planning, right? So you cannot separate these two. That's why this paper is about how we train the both together, and I'm going to talk on the two modules. So there are two parts. The first one is training, and the second part is deployment. Yeah, obviously there is a training part. If you do simulation, we will have these two parts. And training here, we train the low-level controller, and I will share how we do this. And the difficult part of this training, the low-level control, is actually the curriculum, right? So you saw this policy where it steps on the wall, and it's we can actually step on like a vertical wall, like a 90-degree wall. And if you just tell the robot be trained in such an environment, the robot will just give up, right? So robot will fail all the time. It will terminate. And the problem in reinforcement learning is if you don't get useful data, the policy cannot be trained. So you always need some meaningful data, which means that some successful data, right? So in your data pool, you want some successful data and some failed data, and that's how the policy gradient works, right? So you want you train your policy towards the good samples, but you only get the gradient if you see both the good samples and bad samples. And that's why training a control policy is difficult for really challenging environment. Because if you just start training the robot in the challenging environment, it will fail all the time. So what people do is do the curriculum. So it starts with a easy map, and you start to increase the level of the map, and then yeah, then hopefully the policy is trained well in the easy map. Then we gradually increase the difficulty. But there are few problems. So first, you have to control the difficulty. But it's not clear how you do it. Okay, and there are some tricks you can do, or some heuristics. One way is you check the failure rate, well, success rate, and if the success rate is high, you make the map more difficult. If success rate is low, you make the map easier. Okay, so you can do these heuristics and try to provide the right difficulty for the policy training. But here is another problem. Uh, the map is complex, and you cannot just describe it with one number, right? So you want to control the environment, but the map has many different parameters. And how would you choose the difficulty, right? Because this difficulty is multidimensional. And for the jumping motion, like what I presented, we and so if it's like a stepping stone problem, then there's a 6 degree of freedom between the previous plate and the next plate. Okay, and what we are interested in is sampling the distribution between these consecutive plates. And if we just look at the two consecutive plates, then yeah, we narrow the environment down to 6 numbers. Well, it's actually consecutive six numbers. So for each plate we have 6 numbers, and uh, these numbers are actually conditioned on each other. So which means that we don't get a nice uninormal distribution, but what we get is correlation between the parameters. And actually, it's not just correlation, but actually we see nonlinear distribution. So yeah, actually there is no guarantee that these parameters are linear distribution. So we learn this nonlinear distribution using CVAE, um, which is a neural network structure that learns the distribution of a function or distribution over variable. In this case, the variable is this 6-dimensional parameter, right? So, so this is an example. So we describe this map using six parameters, or these consecutive 6 parameters, and we plot the distribution of the 6 parameters. So initially, we see this. So initially, we see some default distribution, and see here too. And as we train the control policy, these distributions represent successful data, right? So any points in this within this set is successful. So and of course, the actual distribution is 6-dimensional, and I'm only showing you the 2-dimensional cut, right? So the actual distribution will be more complex, it will be 6 dimension, but I'm just showing the section of 2D section of that distribution. And we see these distributions evolve. So what we are doing is we train the policy to overcome map like this. And as we train the policy, we train the distribution. Distribution that if the map is successful or not, or successful, the probability distribution represented by CVAE. So which means that after we train it, we can evaluate. If we have a map, then we get the probability that the robot will succeed there or not. Okay. So once we have this distribution, then in CVAE, we can describe this distribution with one number, basically just increasing. Uh, so we can sample outside of this distribution, then it will be the success rate will be low, right? So here we can control the success rate. And this distribution contains this nonlinear distribution of the parameter distribution, that's a successful parameter distribution. So this is capturing the nonlinear nature of this distribution, and we can also easily sample from this. And this is the result. So we, from the initial policy, we train the distribution, and as we train the policy, we train this distribution together. So what we are doing is we train the policy, and we train if the robot will be successful in the map or not. And from that distribution, we generate the map. Then we train the policy, we update the distribution of the map, and so on. So we are keep repeating this process together. And what we get is, of course, the robot will get better in the map. Then the map generator will make more difficult map, and that's why as we update the map generator, so we call this map generator because it's a distribution of the environment, but in the end is used to generate the map. And then we start to see this 90-degree wall where the robot is basically running on a wall, right? Then we also see like a degree up to 120 degree, like angle up to 120 degree, which means it's near it's partially like upside down, right? The robot will do it partially upside down. We didn't do the experiment for that. It's probably a bit difficult to actually make the map, but in simulation this is possible. And if we train that, we can do complex motions. So like and here you also have to note that quadrupedal robot is actually very difficult to do the planning because it has 4 feet, right? For a humanoid robot, you only think about left foot, right foot, left foot, and right foot. But for a quadrupedal robot, you have to take care of all feet or 4 feet. And then we decided to simplify the problem. And this is also from the observation from the nature that actually for a dog and cats, um, they go in very challenging environment. They actually do the bounding, and they do the bounding. And if you observe it carefully, the rear feet actually step on where the front feet stepped. And the reason is clear. The environment is quite complicated, and the cats don't want to memorize all the high field, right? So if the front feed is from the observation from the cat, it taps on the safe place, and for the rear feed, you don't want to memorize all the terrain, so you just figure out the safest foothold, which is where the front foot stepped. So it's if you place your front feet carefully, the rear feet will place on a safe foothold, and this is just like a safe strategy and also less mentally fatiguing strategy, and that's probably why they do it, and that's what we do too. So we when we do the photo planning, the rear feet will always touch where the front feet step, and it's also bounding. So the front feet and the left foot and right foot, they are quite close to each other. So we treat it like one foothold. So in the end, for one step, you just plan one foothold. So that's how we actually narrow down the search space. And this kind of simplification actually is not much it's not much penalizing in terms of performance. So we also tested it in different environment where it's like bumpy and so on. So I don't have the video here, but it worked well. And I will also show you more video. And so what I just presented is if you have this kind of stepping stone environment, you can we train the low level policy that step on this stepping stone. But then, so we also generated we also trained the map generator, which was just to train this low level policy. But then now we should figure out if we have complex environment, we should also figure out where the foothold should be. So these low level policies just follows the footholds, the planned footholds, but we have to plan the foothold somehow. And that's what I mentioned about this the planning. So if you have a complex environment like this, we actually do sampling-based foothold. So we first just generate random trajectories, multiple foothold trajectories, um, and we do set consecutive filtering. Here, what I mean by consecutive filtering is instead of using one big neural network to determine or evaluate if the trajectory works or not, we use smaller network or some heuristics to reject bad samples quickly. Okay, so each filter is not about performing the best. It's about being very lightweight and reject obviously bad samples. Okay, and when you have these light filters in consecutive way, then you can do very fast filtering. So so for example, here I think we do yeah, actually I don't remember from the name, but we have one sample, one filter where checks the standard deviation of the terrain around the foothold, just to check how bumpy the foothold is. And we have another filter, which is the neural network that checks the collision. And of course, that neural network will be heavier than simple heuristics, and that's why it's placed at the end, right? So you also have to place them in a way that you put the heavy ones later to optimize the computation. So, but when you do all of this, but you're still not sure if it's actually physically feasible or not, right? So what we do in the end, we actually run this in simulation. So because we have RISIM, which can do this fast trajectory sampling. So as the robot runs, it simulates forward in time, try different I think like 3 or 4 footholds ahead, and check the reward from that trajectory, and also any cost occurring during the trajectory. Then you can simply pick the best. So yeah, actually that's what you're seeing. So as the robot runs, and of course this runs in real time, right? The simulation is really fast. We evaluate 8 trajectories, and in real time, we figure out the best trajectory. Then if you, yeah, combine this with the low-level controller, then you get like the ultimate never failing controller that goes in. So we even tested with other terrains, but we just created this terrain to visualize how robust this is. Yeah, so angled terrain, slope terrain, like step like terrain, pillars. So here is also nice because it avoids the pillars because we also do the collision checking on the foot, right? So it naturally avoids this foot the pillars. And when we put it on the robot, we get motion like this. Here, we are doing real-time photo sampling, so we can just create any map, and of course, if we have these random boxes, we can have any map, and you just command to go to the end configuration. Then you will sample all these trajectories together. And here, of course, the planning is quite easy. These videos are mainly for demonstrating the low-level controller, the performance of the low-level controller. Here we command the robot to go to this the yellow spot at the end. The robot, yeah, is real time doing the sampling. First like consecutive filtering, then sampling. Then yeah, this is also the same where so here the robot will just sample foothold on these paths, and it's kind of like the planning is not difficult here, but what's difficult is the control. But because we train this a in an environment where we generate these maps just for just the right difficulty, we basically increase the performance. We boost the performance of this low level policy. And here, like the robot is here. We command the robot to go to this yellow spot. This like it looks kind of small here, but you can see my cursor. Then it automatically generates the yeah. So this one too. So you have the robot is here, and it commands the robot to go there. It automatically generates the plan. So one of the so you might ask this question. So how they do the mapping, right? So actually, the robot is not doing the mapping. We give the map, and it's also some maps actually impossible to do. So for example, the map here, uh, the robot is quite low, so it cannot see anything on top, right? So without the map, the robot it just will refuse to jump on top of that box because it doesn't know what's there, right? It doesn't even know it can step on there. Uh, and also for problems or some maps like so maps like this is also like a leap of faith, right? So you jump on top, and like because you need momentum to jump to the next step. So on top, if there's nothing on the other side, the robot will fall and break, right? So without giving the exact map, actually this map is impossible because visually you don't see on the other side. And also what we figured out is for these dynamic motions, we need a gimbal mechanism so that we actually control the camera motion. Otherwise, the field of view is too small and it's not going to detect the ground properly. So that's what we lacked in terms of hardware. And yeah, also other problems like at this speed. So like this kind of high pitching motions, there's too much motion blur. So you don't actually get the meaningful camera data. Then you need like high speed camera, and so it's getting complicated. So that's why we actually we gave the map to the robot, but this paper is mainly about planning and control. So we didn't spend much time on the mapping part. Okay. And yeah, maybe I talked about this briefly. So this work was so most of the reinforcement learning work is on hard ground because like even rising is rigid body simulation, so you can only simulate a rigid ground. And same so the Mujoko the developers say that Mujoko is soft contact. Well, actually, the soft contact is different soft contact from this one because that soft contact is relaxed from rigid body simulation. So it's original rigid body simulation, but they relaxed in the contact solver. So in the optimization process. So then the consequence is that for every step you take actually is kind of different soft contact. The behavior changes quite dramatically. So when we simulate our robot on Mujoko, like in Mujoko environment, sometimes the feet penetrates the ground really high. Sometimes it acts almost like rigid ground, and the behavior is quite like unknown, like quite like chaotic in my eyes. Uh, but that's just because it's very difficult to simulate soft contact contact model. Uh, yeah, because we need very to simulate properly, we need very small time step, and we also have to understand this compliant behavior because it's not just spring damper model, right? And that's why what we wanted to break in this work, just so we developed a physics engine for this soft granular like medium. And there has been some work. You might seen this work where they have the single hopper keep jumping on this soft terrain, and it learns the well, it identifies the terrain parameters, the soft contact parameter, then it makes the robot jump higher and higher through optimization. So there was previous work, and also there has been work that just works on sand without explicit modeling, and this is possible because uh, uh, if it's kind of wet sand or it's kind of hard, and also if you're not running on the sand behaves quite rigid. So when you step really hard, it starts to break, then you see the soft behavior. So we are interested in high-speed locomotion. And that's why we wanted to simulate the sand, and yeah, we had to make this model. And for the proper physics of sand simulation, uh, you have to integrate over the surface, and definitely that's not what we want to do because that will take too much time, right? So we developed a model where we approximate the interval knowing the shape of the foot, because we're not actually doing sand simulation, but we are just doing sand to the interaction between the sand and our robot's feet, right? We only interested in the feet and sand interaction. And because we know the shape of the feet, we can do like a tailored simulation for that feet. And this model is of course not from scratch. We also this model is inspired by previous sand model simulation. But what we really changed is that optimize the simulation because we know the shape of the feet. And once we do the sand simulation, we can uh, simulate different sand. And of course, we need like small time step, but and the simulation is quite fast, so that's kind of okay. So here we simulate a different sand. We use reinforcement learning to train a policy. In the simulation environment, we vary the sand parameters so that we give varieties of models to to the policy, like the policy training, and the policy is trying to estimate the parameter of the sand while it's training, right? Then we can have an adaptive control. So when we deploy the controller, we have a this parameter estimation, the sand parameter estimation, where it estimates the parameters of the sand, then fed it to the control policy, and the control policy is now conditional on the sand parameters, so that it can make proper behavior on that terrain. So actually, we have a video on this running. We can also do the transition because we are estimating the hardness of the sand real time, right? So in the network, is estimating the sand properties. Of course, we need like a couple of steps to properly figure it out. Like we have to step on it in order to figure it out. But at least we can do that. Like after 2 steps, we can figure it out. And of course, if you have like sudden transition between hard sand or hard ground and sand, that can be quite difficult. But if it's a smooth transition, then it's quite robust. Yeah, here we also test on soft sand, like kind of hard sand. We also tested on air matrix, grass field, hard asphalt, running track, and so on. So we see all these different parameters, and yeah, and it can run on that sand because it's keep estimating that parameter. Okay, switching gears, we have another topic. So this work, we are interested in manipulating the object, but we want to manipulate very hard, well, heavy objects. The spot with the arm, but this arm can lift about 3 kilograms when the whole assembly is like over 40 kilograms. I think I don't remember the exact number, but it's like probably over 40 kilograms, right? So that robot can only lift 3 kilogram like object, right? But what we can, so like in industry, we want to manipulate heavy objects, and there's one obvious way. You just make the robot push the object. So yeah, so what we want to do is we want just make the robot push this object such that we locate or move it to the designated location and also the designated orientation. So you see this green and red bar, you want to align them with the green and red bar on the ground. And how do we do that? And actually, the difficult part here is that we have random boxes. So you also want to estimate the property of the object that you're pushing. And also the shapes are a bit different, right? But we cannot like provide the information every time. So the robot should figure that out while it's pushing. And like the basic idea is same. We train an encoder where yeah, it's trained in a teacher and student framework where it's trained to estimate the property of the object, and the properties are the shape of the object. So here we have two types, box and cylinder. Actually, the robot doesn't even know if it's a box or a cylinder. But of course, if it touches, then it knows if it's a box or cylinder. And there are 6 parameters, geometry, so basically the dimension, mass, inertia, drag coefficient, center of mass, and friction coefficient. So it doesn't know any of this. It has to figure that out while it's pushing the object. And here I was also surprised, but what we are using is just locomotion policy as a low-level controller, and the high-level controller is just telling the robot where to go. So it's not a special, so high level controller is, but the low level controller is not a special controller. It's just a locomotion controller that follows our command. So forward velocity, lateral velocity, and turning rate. So this controller is just taking these three commands and follow those commands. And the high level controller knows where the object is and command the robot how it should push the object. Wow. So basically just giving three velocity commands to the low level to the low level controller. And then we can manipulate so here we so the robot is 27 kilogram. The object is 19 kilogram. And we fill it with water, so it's the center of mass is keep shifting. So it's over 2/3 of the robot's weight, so it's almost 70%, and it still can push the object, and also it knows how to orient the object, right? So it's a round object, so you have to use the friction to turn it around, and the robot knows how to do that. Yeah, because it's trained in simulation to do so. And as you see, like the behavior of the robot is just locomotion, like it's just following the velocity command from the high level controller. We tested 45 different combinations. So basically, we change it to different size. Change the size of the box. We put different objects inside to change the mass and the center of mass, and also the inertia. Because we are using different objects, the friction coefficients are different. So there are like different combinations. We tried 45 combinations, and all of them were successful. And of course, all of them are successful because, like, if robo pushes a bit hard, then it knows that it has to go around and crack it with small pushes. And yeah, so it works robustly, even though like the geometry can deviate a little bit from perfectly cylindrical or perfectly box objects. Okay, and yeah, so on another topic. So in this work, we did this planning work, but if you want to use it in the real world, we have to do the semantic we have to give the semantic understanding to the robot, or like the ability to semantically differentiate the world around it. So what we want is if the robot is here, it sees the environment and it figures out if the robot can walk there or not. So basically traversability. And this traversability is not just geometric because the street or the road is also traversable in terms of geometry, right? If you look at the geometry of the road, you can walk there, right? But it needs that semantic information to know that that you cannot walk there. So yeah, so we need this RGB camera. It sees the environment and segment the environment. But then what's the objective, right? So how do you determine if it's traversable or not? Like we have to define this traversability first. And the way we define it is the traversability is the probability for a human to walk to on that terrain. So if I take a picture in front of me, what's the probability that I will go over the terrain in this picture? That's the definition of the traversability here. So that means that if a human is standing here, you will have, let's say, a 70% chance to go across the pedestrian walk and maybe 30% chance to go to the sidewalk. Okay, well, go to this continue walking on the pedestrian walk, right? So then this terrain becomes red, The cone is blue, so untraversable, and then we can easily mark if it's traversable or not. But then we again have the same problem that many other labs have. How do we get the training data? Um, it's it's actually very difficult to get the training data for this kind of problem because I mean, you need to do the hand labeling, right? And we don't want to do the hand labeling because we have like small number of people and all of them are students. They want to do the research. So what we do is we just mount a camera on a human, make him walk around the campus. Actually, not just campus. We also went to different places. But the idea is mount a camera and we record the footage around like 1 hour, and we record the video. And in the video, we do the SLAM. Okay, we run the SLAM algorithm. Then we can project the future footholds on the image space. So we see the image. Because we ran SLAM, we figure out the future footholds, right? And then we can do, so once we have the future foothold, we run this in the SAM model. SAM is a segment anything model from Facebook. Then we can get the label. So this network is basically figure out similar terrain that these footholds are. So footholds are like a query and identify similar object in the image, and it will give us image like this. Then this is a label for us, right? Then we get the free label, what self-supervised label. Then we can train segmentation like network to identify if it's traversable or not. And if we deploy this on the robot, I'm sorry, I'm going probably over. Yeah, it's almost time. I like one small topic at the end, then I'll be done. So here you see the traversability image. You see the pedestrian walk is clearly marked red. So to be honest, I haven't seen anything reliable as this. So if you run normal uh, segmentation network, this is the quality you get. Okay. Yeah, it looks quite bad because there are two key difference. The differences between segmentation network and our work. Our work only determines if it's traversable or not. So we are actually solving easier problem, right? So we cannot say that these are bad because we are solving different problem. And also we can collect, we can easily include more data, right? And because this was in KAIST campus, we collected the data in KAIST campus, then it can be more robust. But yeah, so I will talk you more about this because even though we only collected the data at the KAIST campus, we actually tested in different environment where this do you have it here? Yeah, actually maybe I have to show you the video. So yeah, basically, we also tested in different city, so Seoul, South Korea, and we also went to Tokyo, Rome, Venice to collect the data. And you're wondering how we did this. The student went for like a vacation, and he just recorded the video in different cities. Then we use that data to evaluate the performance of our traversability network. And yeah, you can see that it's actually very robust. So this like terrain looks completely different from other terrains, and we can do the segmentation like this. And as I said, we are solving easier segmentation problem because we only distinguish traversable and non-traversable. So we are solving easier problem. And if we just link this to a GPS based system, we get free navigation of free autonomous driving system. So we in the GPS we just click where to go, and the robot just walks there and checks the traversability. Then yeah, so it's we can do map based navigation using this kind of traversability estimation. Okay. And yeah, because I'm kind of out of time, but I just want to highlight the result of this work. Uh, so we recently completed a full marathon with quadruped. So this is definitely the world first and only marathon finisher in the world. And as far as I know, no one finished the half marathon yet, except us. So we finished the full marathon. No one else finished the even half marathon. And we actually ran with a human marathon, ran in human marathon. We participated in human marathon, and there are about 1,600 people ran with the robots. So they're like 1,600 witnesses. And it took about 4 hours and 90 minutes. So like average amateur marathon runner. So it's not it didn't do it didn't won the competition, but it did about like in the middle. But at least it completed the full marathon. And if you compare this to other robots, so here this is our robot Raibo. With this 1500 watt hour battery, it can run for 55 kilometers. And these are the other robots, right? So the best robot other than ours is Unitrix B2. On their spec, it can run 20 kilometers, right? But it's their spec. We don't know if it's really possible or not, but they claim they can run for 20 kilometers. And so how we did this, I mean, it's a lot of work in different design and control. But I'm like kind of running out of time. So yeah, I'll stop it here and try to answer your questions.
Very impressive work. Maybe I can start with kind of a silly question. So in the collecting phase of the camera information in the traversability map, does the human have to put the camera approximately at the same height of the robot, or it doesn't really matter?
We should have probably that will increase the performance, but we didn't do that. So I mean the way we chose the where is the video? Oh yeah, the way we chose the height is so there is like the GoPro accessory where you mount it on the chest. So it's actually quite higher than the actual camera height. But we just use that accessory because it's we can just buy one and mount it. So there's quite a maybe like 30 centimeter difference in height.
Cool, thanks. Any questions from the audience? Please feel free to unmute yourself and ask questions.
I guess I can hop in with one quick one. So, Jemin, I feel like first of all, awesome work, and I feel like you've done a lot of things thinking about having high-level controllers and low-level controllers and mid-level controllers and a lot of really awesome hierarchical systems. Do you have any insights into like where it's best to draw those lines? Like where does this high level policy stop and the low level controller start. I feel like that, I don't know, I just feel like you've done a lot of work in this space, so that could be interesting.
So for me, I think at least the current policy training we are doing it mostly in simulation. So in physics-based rigid body simulation, and when we want to integrate the vision information, we have to use the real world data, and that's the reason where I believe that we have to separate them from the foothold planning level. So the high level should output the foothold, because that will give we can use the vision data then, right? When we have the traversability estimation from the RGB, we can easily integrate that in the foothold planning, because we get the traversability for that exact point. But that's for actually I really don't know how we can integrate this easily. You can build like a very complex simulation where you train both, but then the vision information is not reliable, and then you also need like a very long time computation resource to do the training if you want to train all of them together. So like I think that's the sweet spot of where we have a high level planner that outputs the foothold, and the low level planner follows that foothold.
Cool. Thanks.
Yeah, no problem. Any other question?
Maybe I can ask another question about the agile parkour motion. So it's very impressive that the robot is able to come up with the foothold to traverse this very complex terrain. I guess I want to ask about how does the interplay between the low-level dynamic controller and the footstep planner really connect to each other, meaning that how the foothold planner is aware what capability boundary of the low-level controller is. Can you give us some intuition and make comments on that?
Yeah. So I guess there we have like a bit of room to improve. So the high level planner, so even though like I claim that I think that the best way we do this is using this map generator to know because this map generator information, this distribution uh, includes the low level controller's performance, right? So if we do the planning using this map generator, then we can say that the high level planner uh, is aware of low level controller's performance and do the plan accordingly. But the problem is that these map generators or these distribution networks are quite heavy. If you do the planning here, then if you evaluate all the samples here, then it's going to take too much time. So, and that's why we do this consecutive filtering, where we actually just filter them heuristically. Okay, and at the end, when we have few samples, we actually run the low-level controller in simulation so that it reflects the low-level controller's performance as best as we can. So so this understanding low-level controller's performance part is during the rollout. So when we do maybe here, no, maybe here. Yeah, when we do the planning using simulation, we use low-level planners, low-level controller to do the planning. So it's actually a quite difficult problem because you don't want your network to be to output what your planner will evaluate the trajectory, and if it's very accurate evaluator, then it's going to be heavy. So that's really the motivation of this work. You don't want one network that's very accurate and heavy.
I see. Got it. Thank you.
Yeah, no problem. Any other question?
Hi, I have a question. Thank you for your talk. It's amazing work. So about the curriculum learning approach, how do you know, I mean, how broad can you go in terms of the complexity of basically the scenarios that you include in the curriculum learning? How do you figure out that, or how do you extend if you start like doing easy scenarios and then more difficult in the learning in the curriculum?
So here we in CVAE we add noise, and we can use that a single parameter to determine how far you are away from the distribution. And of course, that part we tune is just single parameter that we tune, but it's actually very easy to tune that parameter because it's just one number. And that doesn't, it's not like, so that parameter is the parameter from the Gaussian distribution. So it doesn't vary that much over problems. So even if we solve another problem, we can probably use the same parameter.
Okay. But if you go, for example, too broad in terms of the complexity, it is not that it starts failing for all the scenarios, and basically you have to a little bit adapt in terms of how the curriculum is being updated.
So yeah, actually we haven't tested how it scales in different dimensions. So what we just presented is for this 6 parameter problem. And maybe yeah, I don't really know actually how it will scale for different dimension. But at least in high dimension we might tune this more conservatively, but we will still make the training progress. So it might take a longer time, but it will still make it progress. And there you can start tuning this number to introduce more aggressive environment and so on. And that tuning is also, you can do it using the failure rate. Because you have like during reinforcement learning, you simulate multiple trajectories, and you see maybe 70% of them successful, 30% failing, so something like this. So if you fix that number, the success rate, then using that you can tune this distribution parameter in the CVAE. So yeah, in the end you have to tune a bit, but it's not difficult. It's just one number.
Okay, thank you.
Yeah, no problem.
Right. I think time is up. Let's thank Dr. Jemin Hwangbo for this amazing talk. And we're going to have our last seminar next month. And please keep tuned for the announcements. And yeah, that's it. Thank you.
Yeah, bye.
Bye.